Hello friends, this is Sumit Ratan, and in this video lecture we shall discuss about stress strain diagram. So first question that comes to our mind as to why do we study about stress strain diagram, why do we need to plot it? For which the answer goes like this. As a mechanical engineer or as an engineer, when we design a machine element or a structure, we need to first define as to what are the material properties that we require. So we need to select the materials based on that. So in order to know the material properties, we need to characterize the material by testing. So for testing or characterization, we need two basic things. First is a specimen, and second is a UTM. So now what is a specimen? A specimen is a small representative of the material itself that we are going to use for design, and dimensions specified by standard agencies like ASTM. So here we are going to see about stress strain diagram of mild steel, for which we'll use a dog bone specimen. Dog bone specimen looks somewhat like this, which has ends flattened and uniform cross-section area to ensure that failures occurs in the uniform cross-section area for us to have an easy visualization. Now second requirement is a UTM. UTM means a universal testing machine. This is a machine in which has two jaws, and the specimen, this dog bone specimen, is held between these two jaws like this and pulled. Okay. So these are the basic two requirements that is required for characterization of the material and to know the properties in order to use for any design. Okay. So at this point of time I would like to clarify an important point, and also there is a misconception among people as to what is the input given to the specimen by the machine or the UTM and what is the output derived out of it, against which the graph is plotted. So people tend to think that input is stress, okay, stress, and output is strain or elongation. So this is a confusion and sometimes misleading. Also in textbooks, sometimes is not clearly defined as to what is the input given to the specimen by the machine, that is UTM, and what is the output obtained out of it. Okay. So if you have a thought that input is stress and the output that we get out of is a strain, this is not correct. Not correct. Okay. What is true is we hold the specimen in the jaws of the UTM and pull it. So the input that is given to the specimen by the UTM is elongation. Elongation. So input is elongation, which is measurable. If elongation is divided by the initial length, it becomes nominal strain. And what is the output that we get out of this is, see, whenever we draw a graph, we draw between the input and output. So input actually here is elongation. The UTM is pulling the material. So let us suppose at 2 mm per minute. Okay. So this is the input that is constantly being given to the specimen. Now what is the output? See, against the elongation that is against the pulling against the elongation that is given to the specimen, the material tried to resist this elongation, and the resistance offered by the specimen against the elongation is the output. So if suppose in terms of load, that is Pi, if we divide this P by initial area of cross section, we get sigma n. So I told you that people may have this confusion that we give input to the machine as a stress and we take strain out of it, but that is not correct. Input that we give to the machine, give to the specimen, or is given to the specimen by the UTM is strain or elongation, against which the material offers a resistance which is plotted on the y-axis. So simply we will just rationalize our coordinate axis by dividing by constants. So when elongation is divided by initial length, we have strain, and when resistance offered by the material in terms of load is divided by initial cross section, we get stress. So now we have defined the coordinate axis against which stress strain diagram can be plotted. So here is the coordinate axis. So on x-axis we'll take elongation divided by initial length, just to match with the textbooks, because the basic input that is given to the specimen by the machine is elongation, and the basic output that is obtained is the load in terms of resistance. So that is only the basic input and output. But since we in the textbook see that the stress strain diagram is plotted between stress and strain, I am just dividing the coordinate axis by some constants. Okay, so this is the coordinate axis against which we are starting to plot the diagram. Now let us have a bigger chart. Now we'll start plotting, for which we need to first define the coordinate axis. I think it is visible to you people. Okay, so on y-axis we will take the stress, and on x-axis we will take the strain. So strain goes along the x-axis, and stress or the resistance offered by the material, nominal stress, will take along the y-axis. Okay, we'll initially assume that the material doesn't have any strain, and obviously the corresponding stress also will be 0. So we'll start plotting the material from point OO, or we'll refer to this point as O. Okay, so as we elongate the material, as we elongate the specimen, we get this kind of a curve. As we elongate the material, as we keep on increasing the elongation, we find that the resistance offered by the material also increases proportionally, and this proportional relationship holds up to point A, which is called the proportional limit. Proportional limit. So the stress corresponding to point A is called the proportional limit. Let us see, it's point A. So we see the basic behavior of the graph between point O and A as linear. The second characteristic of this stretch of the graph is that it is elastic also. Now, since the graph is linear and elastic, as a corollary we can derive that Hooke's law, that is stress equal to Young's modulus into strain, can be applied to this stretch of the stress strain diagram. Now let us further elongate the material. As we increase the elongation, we find that the material or the specimen does not follow a linear curve, but it is a non-linear curve. So the characteristic of the curve between point A and point B is non-linear. See, first is non-linear and second is elastic. So the material or the specimen in the stretch from A to B behaves in a non-elastic manner, but it behaves in a non-linear manner, but it is elastic. When I say elastic, see, the material's behavior between O to A and A to B stretch of the graph is elastic. Means if at any point between O to B, if we stop stretching the material will restore its original dimensions. Material will return back to its original dimensions. Okay. But since the material's behavior here is non-linear, Hooke's law cannot be applied. Okay. So Hooke's law cannot be applied. Hooke's law can't be applied. So here we derive an important conclusion that Hooke's law can be applied only in the linear elastic part of the curve and cannot be applied in the non-linear part of the curve even though it is elastic. Okay, that we have to keep in mind. Now let us further elongate the material. So as we elongate the material further, we find that no additional resistance is offered by the material. No additional resistance offered against elongation. And this behavior of the material continues up to point C. So we saw that from in the stretch of the graph between O to A and A to B, material continues to offer resistance against the elongation given to it. But from B to C we see that the material doesn't offer any increased resistance to the elongation given to it, and it feels as if the material is yielding, because of which point B or the stress corresponding to point B is called yield stress. Also, the stretch of the curve between B to C is called perfectly plastic. So from O to A and A to B, material behaves in an elastic manner. That means if at any point we leave stretching the material will restore back its, or the specimen will restore back its original dimension. But if we enter the plastic zone, the material undergoes a permanent deformation. And even if we bring down the stress to zero level, the material will not restore its original dimensions and will hold a permanent elongation set in the material. See, we have brought down the stress to zero, even though we see that the material does not come back to zero elongation, means its original state, and a permanent elongation is being set in the material. Okay, so this permanent elongation being set in the material is called as a permanent set. So as soon as we enter into the plastic zone, the material gets permanently deformed and cannot be returned back to its original dimensions. Now let us further elongate the material. See, we need to characterize the material. Here we have come to characterize the material, and we need to stretch or elongate the material until it fails. So we'll further elongate the material to see its behavior, how it behaves after C. So as we keep elongating the material after C, we find that the material again starts to offer additional resistance to elongation. Material again starts to offer increased resistance to elongation. material again starts to offer increased resistance to elongation. Okay, so after C, when we stretch the material, we find that the material again starts to offer increased resistance to elongation. I just forgot to mention that the behavior of the material between point B and point C can be attributed to the changes in the atomic and crystalline level. Okay, for which we'll discuss clear or complete elaboration in material science topic. That is also one of very important topics in mechanical engineering. So after C, we saw that the material again starts to offer increased resistance to elongation, and this resistance comes to a maxima at point D, because of which the stress, if we go parallel to this line, because of which the stress corresponding to point D, since see the material throughout its elongation journey has taken maximum stress at this point D, after it is going to come on a negative slope, the corresponding stress corresponding to D is called the ultimate stress. Generally denoted by sigma U. Here yield stress is denoted by sigma Y. Okay, so material throughout its elongation journey takes maximum stress at point D, and this stretch of the graph between point C and D is called strain hardening region. Okay, now if we further elongate the material onwards from D, we see a trend in the graph that it goes on a negative slope. Here actually confusion arises. I'll just clarify that point. Between the stretch of the graph between point D to point E is actually called the fracture point, where the material actually fractures after coming to this point. So now we see a negative slope in the curve from D to E, and it feels that while seeing the graph, it feels that the material property has deteriorated, but it is not so. Why? Because when we plot the true stress strain diagram, we'll get the exact clarification upon what happens between D to E. Here I want to make one point that in actual the material continues to offer increased resistance in reaction to elongation up to failure. The material actually continues to offer increased resistance against elongation. But why do we get a negative curve negative curve slope between the stretch of the graph from D to E? That can be attributed to a phenomenon called necking. Now what is necking? See, this is our specimen, and locally the cross-section area decreases, resulting in decreased cross-section area. So because of this decreased cross-section area, the specimen is not able to take that much load, and it goes on a negative curve. So here actually the decrease in resistance offered by the material can be attributed to decrease in the cross section area and not to the deterioration mechanical properties. Actually, the material I told that continues to offer increased resistance in reaction to elongation up to failure. So this necking phenomena is prominent after point D, because of which even though the material continues to offer increased resistance up to point E, due to decrease in cross section area, we see that there is a negative trend in the slope of the graph from D to E. Now let us plot true stress strain diagram. I'll just give a briefing upon what true stress is. See, here I had discussed that resistance offered by the material when divided by the initial cross section area, we get the nominal stress. Nominal stress. Now, if we divide the resistance offered against elongation by the specimen by the instantaneous cross section area, this is instantaneous cross section area, we get true stress. Now here one more point is to be made very clear, that also people have confusion about, is what, see here nominal stress is an indicative of specimen's behavior. And true stress is an indicative of material behavior. Okay, so nominal stress is an indicative of specimen's behavior, because we have divided by the initial cross section area. We have not taken the instantaneous cross section area at each point into consideration while devising the formula for stress, but here while deriving the formula for true stress, we have taken the instantaneous cross section areas of the material of the specimen at each point. So here it will give a proper idea about how the material behaves. So now we'll try to plot this true stress strain diagram and we'll see the change in behavior. See now, in the stretch from O to A to B, actually the decrease in cross section area can be attributed to Poisson's ratio, which when drawn to this scale doesn't have much effect. So it will almost overlap. It will be to see also it's like that. So the true stress strain graph will almost overlap over the nominal stress strain diagram. Okay. Now from C onwards, a bit of dissociation in the true stress and nominal stress strain diagram is noticed, because from C onwards the decrease in cross section area is slightly considerable, and it leads to actually, because see here in true stress strain diagram we need to take the instantaneous cross section area at each point of the specimen, although it is difficult to determine at each point, but if somehow by devising any method we can do it, we can draw the stress strain diagram. So it slightly tries to dissociate itself from the nominal stress strain diagram during the stretch from C to D, but you will be amazed to see that between D to E it completely dissociates from the nominal stress strain diagram and goes on a opposite slope, that is on a positive slope. Let us name this point as D dash and E dash. I told you here that true stress strain is an indicative of material behavior. Why? Because at every point we are actually eliminating the concept of having a eliminating the concept of the specimen. We are taking the complete material behavior. So as it was earlier indicated that the material continues to offer increased resistance in elongation up to failure is quite evident from the graph of the true stress strain diagram between the stretch D dash and E dash. So here we can see that the material continues to offer increased resistance against elongation even in the stretch from D to E. But in nominal stress, this was going in a negative slope only because the phenomenon called necking, which leads to a decrease in cross-section area locally. So we'll name this graph as a true stress strain graph. So guys, this is all about stress strain diagram of mild steel. If you have any doubts, you can please write to me. I'll definitely come up with all your solution of all your queries. And if you like the video, please click on the like button and comment and subscribe to my channel. Thank you.